welcome. This is the Physics Classroom Experience with Mrs. Joslin and her students here at Scholé Academy. So we are very excited to have you with us. This event is being recorded, so obviously if you're live, you're here for the whole event and we're excited to have you, but if you happen to be unable to stay for the next hour, not to worry, a recording will be available and we'll make it accessible online. And also if you've registered as a participant, you'll get a direct email as well. So I'm just going to give everyone a minute or two to get into the room. And as you're joining us, you can use the chat box to say hello and let us know where you're coming from. If you are brand new to Scholé Academy, you haven't purchased any classes and you're just exploring, you might put that in the chat box as well. It helps us get to know our audience. If you are a current family, but maybe you haven't taken any classes in the high school yet and you're interested and you're here for the classroom experience, that's great to know as well. There's a couple general things that we'll put into the chat box. If you have general questions, the best way to reach out to us will be support@scholeacademy.com. And all of our instructor emails and bios are available on the website under About Us. So those are kind of some key places if you're new to our school that you'll want to follow on the website. And if you've not yet subscribed to our e-newsletter, you can do that as well on our website. It's under resources, and you'll see there's a link there that just says newsletter sign up. That's the best way to keep in touch with our school. We send that out every Monday. So before I introduce our guest instructor and her students, I do just want to give a brief history about our school. Scholé Academy started in 2014. We are an educational service line within Classical Academic Press, which is a publishing company. And so Classical Academic Press started Scholé Academy as a way to, of course, join the revival of classical Christian education. Classes at Scholé Academy are classical, restful, engaging and personal. So what this means is that in terms of restful, we are talking about contemplative learning, providing time for students to focus on what is most important. We encourage our instructors to identify what are the essential concepts and skills and great books to read. And we hope that learning focuses more on quality instead of quantity, and kind of move away from that kind of cram information, test it, and then forget it and move on. So less is more in some cases when we're talking about restful learning. And then the engaging piece, we, as you'll see today in our science and math department, as well as our other classes, learning is engaging. And so there's collaborative work and there's discussion and there's screen sharing and there's, breakout sessions. So there's lots of ways that we engage our students. When Scholé Academy started in 2014, we had 8 students in 2 classes. We are now well over 1,800 students this year and over 200 course offerings, class offerings, I should say. So lots of opportunities across all of the courses as it relates to the trivium and the quadrivium, in addition to fine arts and common arts. So we have a robust offering and our classes are a la carte, meaning that students and families purchase a class, not necessarily a bundle for a grade. And so our student parent handbook, which is available online, that's a great resource if you're new to us and you're trying to understand our philosophy and our policies and guidelines as it relates to course selection. We also have a tutoring center that supports families with private course instruction as well as supplemental. And then we have Center for Students with Learning Differences. At Scholé Academy, we do believe that classical education is for all students, and we seek to support parents and all of our students with their various learning styles and differences. So we are proud of that aspect of our program. And then we also have summer programs. We will launch those May 1st, along with our largest house, which is St. Raphael School. We have 3 houses of studies specific to 3 Christian traditions: Orthodoxy, Catholicism, and Anglicanism. So we will provide those. St. Raphael School courses launch May 1st with summer, but you can currently see our Aquinas House and Canterbury House of Studies course offerings. Those also are a la carte, and we provide that as a space where families who want to support their student in their further study of Bible and catechism, church history within their specific tradition, as well as music and liturgical elements as it relates to their Christian tradition. Again, if you have any other questions or would like to learn more about Scholé Academy, email us at support@scholeacademy.com. So let's go ahead and get to what is most important about tonight, and it's meeting with Mrs. Joslin. She is a pretty interesting, fascinating lady. She's had time at Mission Control at NASA. I like to lead with that because that sounds very exciting. And it is, I think. But her background is in engineering, and she has over 12 years of teaching and homeschooling experience. So she brings depth and certainly knowledge and love for her students into the classroom. And so tonight you are going to see that in action. And you see here we have a great bunch of students. They are Scholé Academy upper school students who have worked with Ms. Joslin, and they are going to demonstrate for you with this instructor what it's like to take one of our Scholé Academy courses. So with that, Ms. Joslin, I'll pass it to you.
Okay, so thank you for that introduction. My name is Sherry Joslin. I neglected to write Sherry on there. I like to be Mrs. Joslin to the students, but my first name is Sherry, and I live in Fort Worth, and actually a little bit south of Fort Worth in a small town called Burleson, which is about 20 miles south, but it's a suburb, so it's really a big city. And I am a mother of 3. This year we are recent empty nesters. I have 2 sons and a daughter in the middle, and both of my sons are getting married this summer. So I've got a busy year, which is blowing my mind. But anyway, I'm excited for that. They all love the Lord. That's probably my biggest accomplishment, and it's really all God. But they all are walking with the Lord and love Jesus, and are doing really well in their school and professions. My oldest son, he graduated from Baylor. My daughter graduated from the University of Arkansas, and my youngest son is currently at UT Dallas. And they are all they all had STEM degrees. My oldest had a biology degree, engineering. So with that though, I've also been married to an amazing guy, Brian, and we've been married for almost 30 years this year. So I have in my background a hodgepodge of things. I've homeschooled, I have taught in the classroom, we have international schooling experience, we have public schooling experience. So I feel like I personally have gone back to school. So we have a lot of different varied experiences, and I love to share with my moms some of the things that you might encounter in each of those settings. So as far as my teaching and work experience, I did start off out of school. I graduated with a bachelor's of science in electrical engineering, and I worked at NASA for about 10 years. So I worked in the mission control. Some other time I'll share my testimony there. That was also a God thing. The Lord opened the door for that position. But after that, when I started having kids, when my youngest was 2, I quit to raise them. And I tell people, this is kind of my tagline, that children are more complicated systems than space shuttles or space stations. And I think you would all agree with that. So after I quit and my kids were young enough to go to school, we sent them to a classical school. And this was in the early 2000s. So I've been in the classical movement for quite some time. And to offset tuition, I started teaching there part-time. And I began by teaching logic. So I taught logic for about 7 years, and also some math, some algebra. And then that gradually moved into science. But more recently, I completed my master's degree in science and religion. It's a master's of arts, and it's a Talbot Seminary degree from Biola. And what it is it's an apologetics degree, which really it combined the idea of how science and faith are compatible. And what they did for me is they threw all these arguments from any kind of scientific discipline you can imagine. I got physics problems, quantum mechanics problems, chaos theory problems, evolution, biology, philosophy, history, philosophy of science, theology, you name it. So it really, in the end, it really bolstered my faith. And it gave me an awareness of how these students today, when they go to college and they go to university, they need to feel confident in their faith. And so that's my passion, is to instill in these kids just a confidence that the Christian worldview is the best way to live your life and the best way to flourish. And there's no such thing as a conflict within the study of nature and the study of science and Christianity. There's no conflict there. Where the conflict lies is in scientism and people who turn their back in the scientific fields, and a lot of academic professors have. And so that's where these kids will encounter some of that. Why Scholé? Real quickly. I was attracted to Scholé because of Classical Academic Press. I had used much of their curriculum and logic and rhetoric for my classes, and also some of the homeschooling stuff, and also the science, the Novare curriculum. I used that when I taught physics in high school. So I was really impressed with that. And also when I signed up, I little did I know what an amazing community it is. I mean, the community of faculty and staff and students is just really surprisingly close, even though we're virtual. I love meeting with my kids daily, where we're getting to be fast friends. I get supported by the faculty and staff as well. Also, the main thing is the classical Christian curriculum and pedagogy that Scholé offers. And one thing about that is apparent to me, and as a result of my degree, is that science today falls short when its goals don't fall in line with the liberal arts tradition. And that's because without objective truth and without virtue based on God's order, science, just like culture, it falls victim to relativism and scientism. It has no compass. And Scholé, they seek to reclaim virtue and truth in teaching their liberal arts curriculum. And I will tell you, I've seen it firsthand. Just these students' presence, their characters are amazing, and their dedication and desire to learn and love for knowledge. This is really some of the best students. These are some of the best students that I've taught, and I've taught in a lot of different places. So anyway, it's working. So with that, I also wanted to talk about the restful aspect of Scholé. The book that I use for my intro physics class, it is set up to where it will focus on key concepts. Okay, so one of the biggest complaints that I've heard from universities is that the kids coming into physics and STEM, they know how to crunch the numbers, but they don't have the big picture. They don't have the big story. So what the Novare curriculum does is it takes the time to create sort of a mastery of the topic. It slows down and it hones in on key but very, very detailed concepts. And we look at it from a variety of different ways. So with that, I'm just going to let you kind of experience that with the class. And hopefully you'll be able to see some of the elements of tying and integrating in history, integrating in virtue, integrating the kingdom perspective, integrating qualitative and quantitative and purpose. I mean, all these things my kids don't even know I think about when I prepare a class. But anyway, with that, let's get started really quickly. So let's just assume that we've started our class today. Hello, students. I hope you had a good weekend. Typically, I'll ask somebody, tell me something fun. What happened to you yesterday? If you don't raise your hand, I'm going to call on somebody. So somebody tell me something interesting. Yes, Noah.
On Sunday, I went to watch the new movie in the theaters, Creed 3. It was pretty good, I think, generally. And I went with a couple of friends, and that was generally my weekend. And then I had baseball on Saturday.
Okay. So, I wish for those days again when I could go to sports and watch a movie. That sounds like a lot of fun. Anybody else? Anybody else? Anything fun, exciting? Okay. Well, thank you, Noah, for sharing that. Okay, so what I typically do, and what I'm just going to not say that, I will just do it. We're going to take a look at our Canvas. So I'm going to share my screen and share my desktop. And when I do this, it gives me kind of a breather here a little bit. So let me see if I can find where I put that. I closed the window. So this is kind of typical here for me to do that. They get to look at my desktop here. And this is the page that that we would come to first, okay, for every class. And I will click on the modules. And the reason why I'm doing this, I want to make sure I've posted all our homework for today correctly and what we're going to do. So today is Wednesday, and we have a classwork section. So let's take a look in there. And in our classwork today, I'm going to show you guys a PowerPoint, a real brief PowerPoint over Newton's law of universal gravitation. And then if we have time, you will be doing a simulation. And the simulation is what I call a PhET sim. It's by the University of Colorado. Okay. The notes from today, I will post those later. So let me check our homework. Oh, wow. Do you guys have homework? And this is an experience time? Yes, I've given you homework. Okay. So your homework is to submit your gravitation lab sheet along with your notes, but it's for extra credit. Okay, so it's optional, but if you want extra credit for being here today, I would love you to finish it if we don't get done. Okay, so let's go back to our class. Okay. Also, students, I do want you to take notes, so get your notes out. All right, I do this right here. PowerPoint, and I'm gonna make sure that you guys can see this. Let me put that down. Okay, so give me a thumbs up if you can hear me okay and screen looks good. Okay, Jack, thank you. Sometimes I get 2 or 3 slides in or into something and then I realize I'm muted, so I've got to make sure. All right, so the first slide that I have here is a really cool quote. Let's see, Noah, can you read that? I just picked on you, but can you read that again?
Gravity explains the motions of the planet, but it cannot explain who set the planets in motion.
Okay, so that's Isaac Newton right there. Okay, so Isaac Newton is famous for that quote, "on the shoulders of giants." Okay, and here I have a picture of 4 giants. And I know you guys have studied these giants in earlier chapters of the book. So can I get somebody to tell me anything they know about Copernicus? Okay, what do you know about Copernicus? Anything, anybody? Tell me what you know. Don't be shy. Thank you, Joshua.
I believe Copernicus hypothesized about the heliocentric view of the universe, where the sun was the center of the universe.
Yeah, very good. Okay, so anything else about him? Okay, what about Galileo? Somebody tell me about Galileo. Galileo, okay. I am going to call on Jessica. I'm gonna call on you. What do you know about Galileo? And you are muted.
Oops, sorry, can you guys hear me now? Yep. Okay, so I believe he was the one where he put the sun in the center of the universe.
He did. He built on Copernicus's theory, right? Okay. Anybody else about Galileo? Okay. Galileo. Did Galileo get in any trouble? Anybody know? Did he get in any trouble? Okay. Jack.
He did get in trouble with the Roman Catholic Church as a result of essentially he was who insisted that his theories were correct and that the church was misinterpreting scripture. And he, I believe, actually published a book about heliocentric theory after being explicitly told not to. So as a result, he was under house arrest.
Okay, so one thing that I do mention about Galileo when we study him is that the church was the stronghold was actually the inventor of the university, and they ran all the educational institutions, and they were pretty smart. I mean, the professors in the church universities were pretty smart, and Galileo was coming up with some new theory, and so it was resisting the old. So it wasn't quite a scriptural basis that the church had in conflict with Galileo. In fact, Galileo himself, he kind of did some things that he wasn't supposed to. So he brought a lot of his troubles on himself. But he certainly had an uphill battle, and he ultimately won. But okay, so what about Kepler? Somebody tell me about Kepler. Olivia, thank you.
So Kepler was the one who came up with the laws of planetary motion. So just from the textbook, the first one is each of the planetary orbits is an ellipse with the sun at one focus, which is kind of important because up until now, to explain the retrograde motion of the stars, people had thought that there were tiny little, like the planets were going in tiny little circles around the large circle orbiting the Earth.
Yeah, so you're talking about the epicycles, So we'll talk about that model in just a second, Olivia. Very good. Okay, and what about Newton? Newton. Okay, anybody know anything about Newton? I know Jack. Oh, go ahead, Noah.
Well, he did the 3 laws of gravity. He was kind of wasn't the first one to talk about gravity, but he was the first one to come with a formula that worked quite precisely. And he did it in such a condensed form that it was like a lot of the formulas are very simple, but he was the first one to figure out that formula, and that would helped him quite a lot. And he also, I think, worked on the lens. And the first time that he ever thought about gravity was when very common thing was when the apple fell next to him when he was working next to it, because he was on his grandfather's farm, I think it was, and that was the beginning of how he started learning about it.
Yeah, okay, great answers. Okay, so let me see if I can get this to work. Okay, so this is his famous quote, and Ezra, can you read that for me, please?
If I have seen further, Isaac Newton wrote in a 1675 letter to the fellow scientist Robert Hooke, quote, "It is by standing on the shoulders of giants," unquote.
Okay, so this quote says a lot, and he did attribute all the stuff that he learned as being a culmination of what Kepler did and what Galileo did and what Copernicus did and others and what Robert Hooke did. So he didn't say, hey, I'm just the smartest, coolest dude. He says, I'm taking some of the stuff that you have taught me, and I'm going to stand on that, and I'm going to build on that. And that's kind of how the scientific enterprise works in general, is that science builds on what we already know. Okay, so he was also a devout Christian. Okay, so he wrote, oh gosh, so many more things about Christianity than he even did about science. So a lot of people don't know that about Isaac Newton, but he had an idea, the Christian idea, that the universe depends on God's specific purposes. And he recognized that the ancient Greeks had a different view, and I think Olivia kind of brought that up. She was talking about the Earth being in the center of the universe. That was the Ptolemaic view. We've studied that too. But the Greeks also thought about how things went on eternally and how there was perfection and necessity, and there isn't much fun in that. But the implication of having a Christian worldview is that we can study nature just by discovery and not just by rationalizing things as they must be. Okay, so that's a subtle switch in how the Christian scientists, many of them, they were after discovering God's creation. Okay, so Isaac Newton, he also is famous for the mathematical principles of natural philosophy. And in this document, he describes the 3 laws of motion, and he also deduces or it develops his universal law of gravity. And he also, I didn't write this, but he also proves Kepler's planetary motion laws. So when he came up with his gravitational universal law of gravity, he realized that unless it fell in line with Kepler's laws, he was in big trouble. So he not only proved and showed that Kepler's laws worked with his theory, he proved Kepler's laws from his theory. So pretty impressive. And a lot of modern day scientists cannot figure out his math. Okay, he also invented calculus, and they still don't know the logic of what he did. So anyway, this is also contained in that book. So let's see. Who can I? Jessica, can you read this for me? This is a quote written in his book he published.
This most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being.
Okay, pretty cool. Okay, so here is what we're going to study today. Okay, and don't let this overwhelm you right now. We'll break it down. But what Newton did is he was to show, and I'm going to describe the equation here, how the inverse square law of attraction, that's what it could be called too, had many necessary mathematical connections with what we observe in the motion of the planets. Okay, so that's just kind of a big bubbly way of describing his equation here, and we'll go over it a little bit more in a minute. Okay, but what I do want to show you, I'm going to go back, is there's a constant in here, and this constant is the gravitational constant. All right, so this was unknown to him at the time. It was eventually discovered, and it was discovered by a man named Henry Cavendish, and we'll talk about that in a minute too. But the importance of this contents from a kingdom perspective, and when I say that from a Christian worldview, is it is one of what we call fundamental constants of physics. Okay, so it is one of the many constants that describe how things behave in our universe. So there's electrical charge, there's a speed of light, the masses of a proton, electron, and that should be a neutron. I have a typo in there. So those, oh dear, what did I just do? Don't mean to do that. Hang on one second. Go back here. Okay. So what this demonstrates, and what Christians often describe when they see constants that impact exactly the life that we live, is they're referred to as fine-tuned features of the universe. In other words, they're on a razor's edge. So if that gravitational force constant was a little bit off, or if the speed of light was a little bit off, or the Earth was a little bit closer to the sun, then the necessary conditions for the existence of our life wouldn't happen. Okay, so that's kind of a big deal for Newton discovering one of those. Okay, and then one final thing before we move off into our examples, and this is a really cool quote. So I'm going to ask, let's see, who hasn't spoken much. Lotus, can you read that for me?
Okay, Newton's laws of motion combined with his law of gravity allow the prediction of how planets, moons, and other objects orbit through the solar system, and they are a vital part of the planning space travel.
Keep going.
During the 1968 Apollo 8 mission, astronaut Bill Anders took this photo, Earthrise, on their way back to Earth. Anders remarked, "I think Isaac Newton is doing most of the driving right now."
Okay, so his laws are why we can do space travel. Okay, all right, so that's the end of that. Now let me push escape here if I can get it to work. I'm going to stop sharing, and I'm going to move on to my PowerPoint. Make sure I got this. Takes a minute. Okay, so my notes look a little different today, guys, because I filled in some of them for us ahead of time, but we're going to go through the laws of motion, and let's just step back because these laws of motion are combined to determine Newton's universal law. So somebody tell me what the first law of motion is. Okay, Olivia.
An object at rest will stay at rest, and an object in motion will continue moving in a straight line at a constant speed unless acted upon by an external force.
Okay, so I kind of wrote down what you, let's see if I can do that again. Okay, so an object at rest remains at rest. Let me get a color here. Okay, so an object, so one object at rest remains at rest. And this should say an object. And an object in motion continues moving in a straight line at a constant speed unless it is compelled to change by that state of forces acting on it. Okay, so what about Newton's second law? Anybody? That one. Lotus.
The acceleration of an object is proportional to the forces acting on it.
Okay, so you gave me the the acceleration of an object is proportional, and I'm going to have to change my pen here because it's not doing what I want. Okay, proportional to the force acting on it. Okay, very good. And what about Newton's third law? Noah.
Every action has an equal and opposite reaction.
Okay. For every action force, there is an equal and opposite reaction force. Okay, so you guys have given me a description of all three of these. Now I'm going to ask you to give me a way or a formula, a way of quantifying these laws. Okay, so when I say quantifying, what do I mean by that? Can somebody tell me what the difference between quality and quantity is? Let's see, Olivia.
So quantity kind of looks at more observing through numeric observations, like what you can put into numbers, and qualitative like observation more looks at like the qualities of things without the numbers.
Perfect. So Olivia, I'm gonna pick on you for the first one. Can you give me, look at those big eyes, can you give me an equation for the first law? We did this a long time ago, so if you don't get it right, I'm okay, but think about it. An object remains at rest and an object in motion continues moving in a straight line. Okay, did that again. So think about that. Does anybody else know? Jack, you got kind of a half hand. What do you think? How could we describe that?
I believe from what we went over in class earlier, it says that an object doesn't accelerate if there is no net force. So the equation is just net force equals 0, and I believe the symbol for net force in addition to the F is yeah, it sort of looks like an E like that. Yes.
Okay, and that equals what?
That would equal 0 as there is no net force.
Okay.
There's no acceleration.
What does net mean, Jack? What's net?
Net force is a force that isn't cancelled or balanced out by something. So it's a force that's actually able to act on an object.
Yeah. Awesome. So if it's still, it's going to stay still unless there's an extra force pushing it. If it's in motion, it's going to keep that same speed unless something boosts its motion or stops it, right? Okay. So Newton's second law, let's see, Noah, what is the equation for Newton's second law?
Acceleration equals force divided by mass. That is one way of writing it. There is two other ways of writing it. Force equals to mass times acceleration. And the third way is mass equals to force divided by acceleration. This is because the mass is kilogram meters and seconds squared. The way that the formulas are written is that we can divide and times to get what we what we want every single time.
Okay, so depending on what you want, okay, but the way that the book uses it is, or writes it, is usually acceleration equals force divided by mass. And the way that you're going to probably see it more in life is force equals ma. Okay, so this is kind of an aside question. So what is A? Somebody tell me what A is. A is acceleration. Well, I just answered that. What do you know about the force of gravity that we've learned? What is acceleration when we are talking about the force of gravity? Okay, somebody tell me. So Lotus.
So acceleration due to the force of gravity on Earth is 9.8 meters per second squared.
Okay, so, and we write it F equals mg, and we talk about that force as being the force of weight, right? So the force pulling on you, your weight when you step on the scales, is your mass times the gravitational field strength of Earth, which is, what was that, 9.8? Oh, I just write it, meters per second squared. Okay, so I'm telling you this because we're going to use it again in a minute. All right, so third law. Okay, who wants to try that one? Anybody? This one's a little trickier. Joshua.
I believe it was, I went over earlier, it was force 1 times force 2 is directly or equal to force 2 times force 1. It's an equal outcome from both equations.
Okay, so the way that it's not actually multiplied together, but it's the force of one object on another object equals the force of the other object on the first object. Okay, so I'm going to show you this little picture here. If I can do it. Okay, so here I have let's try another way here. Okay, here I have a hand against a door. Okay, so what Newton is saying here is that if you have a force being exerted by the hand on the door, so this is the force of the hand on the door, this force of the hand on the door, that's the same thing as the force of the door on the hand. Okay, so the third law is different from the other two because it's talking about how many objects. The first two laws apply to one object, but the third law applies to how many objects, Joshua? 2. So it's applying to 2 different objects. Okay. All right. Very, very good. Okay. So the third law, the fourth law, does anybody know what Newton's universal law of gravitation is? Anybody know it? I think Noah kind of said it. Jack.
Every object in the universe is attracted to every other object in the universe.
Yes. Okay. So it says Newton's universal law of gravitation isn't just about apples falling. It states that every object in the universe pulls on every other object. Okay, so I want to do a thought experiment here. And I want you guys to think about how Newton could have come up with that. What do you think? Noah.
Well, he could think that he's getting pulled to the ground, so is that apple. So the greater something has of gravity, the more likely it is to be pulled down. So if he is getting pulled down, the apple's getting pulled down. So I would think he makes the comparison. We're both getting pulled down. Why are we getting pulled down? And does everything else equal to that?
Ah, you are on the right track. Okay, so I'm going to draw a little picture here. I kind of already did. If I can get it. Okay, so here's my world right here. Okay, and this is several trees around the world. And what we noticed, or what he noticed about the trees, is that, let me see if I can get the right color, and the apples, is that the apples all fell toward the earth in a radial direction. Okay, so they're all falling in a radial direction. So he noticed that, okay? And then he thought about the moon. He looked at the moon up there. There's my moon. And he thought, well, I wonder if the moon is also falling toward the earth in a radial direction. Okay, and he was right. Okay, but why, if the moon is like the apple, if it's accelerating down, why isn't it crashing into the earth? Why doesn't it hit us? Anybody? What do you think? Olivia?
That would be like his third law of motion, like every for every action first, there's for every action first, there's an equal and opposite reaction first, or his universal law of gravitation, because just as the earth has a pull on the moon also has a pull on the earth.
But Olivia, wouldn't that make it just smash into each other quicker if both the forces are pulling on each other?
But his third law says that they're like equal.
But they're okay. Let me tell you, I'm going to veer you a different way. Okay, so what is the earth doing? The moon doing? It is moving around. It's going around. Okay, and so this speed, this velocity or speed is so fast that it keeps it from falling in. So that the velocity going around is bigger than the pull right here, or the acceleration. We'll say the centripetal acceleration of the moon. Okay, this concept right here, if you really want to know, you need to take my honors class, because we go into that. Okay, but what I want you to know now is that because it's spinning around so fast, if let me just ask you this, if that force were cut, if this were cut, the moon would continue to go off in a straight line, just like his first law says. Okay, but it keeps trying to be pulled in, but it's not. Okay, so he observed this, and then he thought, well, if the moon is being attracted to the earth and the apples are being attracted to the earth, what about the planets and the sun? So he got bigger and bigger and bigger. He started thinking about that. Okay, so now I'm going to ask you, or just kind of tell you this. Okay, so people by that time already knew some things, even from antiquity. Okay, so there was a guy named Erasmus. He lived in 240 BC. Does anybody know what he discovered? Does anybody know? Erasmus, he was an old Greek guy. Anybody know? He determined the diameter of the earth just by looking at the shadows. Okay, so he determined, no, it's not gonna work. Let me try this one. We'll go green. The diameter of the earth. So Newton would have known that. Okay, he also would have known the distance from the earth to the moon. He would have known that. He knew, thanks to Galileo, how fast an apple accelerated. So a lot of people think that it was Newton that discovered the gravitational field, but it was actually Galileo who measured how fast an apple would fall. An apple would fall to the ground. So he knew the acceleration of an apple. Okay, and let's see, they also knew the angular speed of the moon around the earth. The moon around the earth. Okay, so Newton knew all this. Okay, and he got this brilliant idea to compare, and this is a little bit about what Noah was saying. Okay, so he had this idea to compare the apple to the moon and the earth. Let's see. Let me just write this. So he took the acceleration of the apple and the acceleration of the moon, and he compared it to the distance of the apple to the earth center and the distance of the moon to the earth center. All right, I don't know how the math works, so I kind of looked at an easy way to explain it, but by this very notion, he was able to figure out, using his other laws, that the force of gravity, or the force pulling it, is proportional to the mass of the two objects, the moon and the apple, divided by the radius squared. Okay, what I did find out, though, is that Kepler had an argument with him, because Kepler accused him of stealing that idea of r squared from Kepler. But anyway, who knows? Okay, so anyway, so he figured out that there was that they were proportional. What does it mean to be proportional? It means that they're almost equal, but there's a little value there that will make them equal. So it's called a constant of proportionality, and that ended up being the constant, the gravitational constant G. Okay, so one thing about the gravitational constant G, another thing is that it was a placeholder for Newton for years. He knew, but he didn't know how to figure out. Most of his work was without instrumentation. You can't really measure gravity from the moon, etc. So he knew it was there, but he didn't know what it was. And it wasn't until 100 years later that Henry Cavendish figured out the value. And he figured out the value to be 6 times 6, 7 times 10 to the negative 11th. Okay, and the units are Newton meter squared over kilogram squared. Now, the thing that you should recognize about this number is it's really, really small. Really, really small. Okay. All right. All right. So let's take a look at his equation again. So once we put it all together, I'm going to rewrite it here. And as I rewrite it, can I get Jack? Can you read the paragraph I've written there?
Magnitude of the gravitational force that an object exerts on another object is directly proportional to the product of their masses and inversely proportional, where the bomb is covered, to the square of the distance between them.
Okay. So what I'm going to ask you here is what do we mean by inversely proportional? Any ideas? Inversely proportional to the square of the distance between them. What do I mean by that? Inversely proportional. Olivia.
Well, if they're like directly proportional, that means, say, as like one thing goes up, then the other thing goes up. But if they're inversely proportional, doesn't mean as like one goes up, the other goes down.
Yeah. So in the inverse of R is 1 over R. So that's what it's talking about there. And where this is going to be important is when you guys do your little lab. Okay. So if I give you an equation, you know, what's really funny is I have an hourglass here and it kind of got stuck there. I need to click it. Time is not working through my old-fashioned timepiece. Okay, so how are we doing on time? We're still okay. I've got a few minutes. Okay, we may not get to the lab, but in your lab, what it would have asked you to do is to look at the proportionality of this constant, and this is the qualitative aspect here. So Olivia, I'm going to ask you. You told me that that the inverse relationship is the R at the bottom. So if that R gets bigger, what happens to the force? If the R gets bigger, can you see that? If the R were to get bigger, can you qualitatively see that?
If the R were to get bigger, then the force would get smaller.
Yeah. Okay. So Ezra, why would the force get smaller if the distance between the two objects got bigger?
Because I guess there'd be less to hold on to. Because I guess if the force went onto if the distance got greater, then the force would have to stretch longer.
Yeah, it kind of makes common sense, right? So the further you get away from the gravitational field, the weaker the force. But if you look at it this way, okay, say if I have a fraction here, say if I have 2 over 4, and I know that an equivalent fraction is 2 over 4, it's the same number, right? But what if I change the denominator, Ezra, to 8, and I still want an equivalent fraction? What is the numerator going to be?
If you wanted so if you're adding it like 4 over 8, or you want 2 over 8?
Okay, look at this. If I have 2 8ths, what is an equivalent fraction? What would, if they reduce to the same, what would my numerator have to be?
4.
4, right? Okay. So if I make this bigger, okay, maybe that wasn't really okay. I asked you the wrong thing. I was thinking of something else. So let me hold back. Let's go back here. So let me just do it more simpler. Okay, so what if I have a fraction here that is 1/100? Is that bigger or smaller than 1/5? Ezra.
That would be 1/100 being smaller than 1/5.
Okay, so what I'm trying to get you to see here is that when the denominator or the distance gets bigger, the force is going to get smaller. Okay. All right, but when it's closer together, just like you were saying, then the force is going to get bigger. So that's kind of a qualitative little approach that the lab would have shown you how to do that. Okay, so now it's your turn. I want you guys to do this next problem, and we're going to use the equation, but we're going to use it on a small scale. Okay, so write it down. Everybody write that down. You need to write the equation because we're going to use it. Okay, and get your calculators out. And then you also need to write the value for G. So make sure you've got G there. All right, give you a second to do that. All right, fast. Okay, so now this is the example I want you to work, and I'm going to read this. Okay, so while you're sitting there watching this lecture, there's a gravitational force that your computer, your 10-kilogram computer, that's its mass, sitting on the table in front of you exerts on you. Okay, assume that your mass is 70 kilograms and the distance between you and the computer center of mass is 6.60 meters. What is the force exerted on you by your computer? Okay, I'm going to give you a minute to work it out. Okay, I know I probably didn't give you enough time, but let me call on Lotus. How would you work this problem?
So I guess you just plug in, so mass 1, you could plug in 10 kilograms. Mass 2, you'd plug in 70 kilograms. And then you'd multiply that by the gravitational constant 6.67 times 10 to the negative 11th. And then divide that by 0.6 squared.
And then if you were to do that, I'll just save you the time. You should have gotten a value of 1.3 times 10 to the negative 7 newtons. Okay, so is that a big number or a little number, Jessica? This number right here, is that big or little? Is that a little force or big force?
That's our little force.
Yeah, it's a really little one, okay, because you've got a bunch of zeros in front of that one. So if you were to compare it, it would probably be about the same as like maybe 3 specks of dust. Okay, so your computer is tugging on you, but it's negligible, right? Okay, all right, and then also you're sitting and you've got a force of gravity pulling you down, so that's overcoming, just like the moon's velocity pulling in or away, it's overcoming the weaker force. Okay, so then one more. Okay, and then we'll stop on this. So let's do this one. Okay, calculate the Earth's gravitational force on you. Okay, you're given a few things here. Your mass is still 70 kilograms. And the Earth has a mass of 5.97 times 10 to the 24th and a radius of 6,370 kilometers. Okay. for sake of time, let me pick on Jack. How would you go about this?
Okay, so in this case, you want to calculate the force of the Earth on you. So in this case, the Earth's mass would be mass 1. And then, so it would be G M1 M2. So G 5.97 times 10 to the power of 24 kilograms times 70 kilograms over R squared, or 6,370 kilometers squared.
So you'd plug all those values in, and what you would end up, and I'm just gonna do this really fast. Okay, so you would end up with 687 newtons. Okay, and if you were to do this the old-fashioned way, so you're on the Earth, so you're going to do F of weight equals mass times G, and you were to plug your mass in of 70 kilograms and use the gravitational force 9.8, you would come up with the same value. Okay, so I'm going to end it there. We're not going to have time to do our PhET simulation, but you guys still can do that for extra credit. I'm going to hand it back over for Q&A.
Thank you, Mrs. Joslin. Thank you, students. This has been great. We're going to take a little bit of time here to answer a few questions that have come in. I want to start with, I think, probably the question we get the most about, which is labs. So, Ms. Joslin, could you talk to us about how do you do class labs? Are they in class, out of class? How do you balance types of work done in class versus on their own?
Okay, so a lot of times we will do a lab out of class, and when I say a lot of times, how do I say this? The lab manual that goes with the Novare book is really best suited for a classroom. Okay, so I found that out this year, and because of that, we modify it a great deal. And I'm encouraging people not to buy their lab equipment until the start of class, and then I will give you ample time to figure that out. But another thing too is because the kids are at home and they're in individual spots, when I put them in lab groups, I will take the time out of my class to let them plan together. So we'll have a class period where they can plan and they can think about how they're going to do their lab. And say they want to discover the different types of heat transfer, okay? And say they want to boil some water and put something in it and measure the temperature. Well, they're gonna have different equipment to do that, but the basic stuff is the same. So they'll come together, they'll plan it together, and then they'll do it at home on a weekend, usually on their own, and then come back and compare their results. And sometimes that's done out of class, the comparing part, they'll have to meet somehow. And then other times I will give them time in class to do it. A lot of the labs I do are simulations. I wanted to show you one today. There's some amazing stuff online from universities that will simulate a lot of the labs that we typically do in a classroom. So I'm very aware of the time consumption and also the supervision that's required for some of the lab work. So if there's a lab that requires something dangerous like fire or whatever, I will make sure that a parent is available too. So you did.
Could you also talk about, just on average, the homework expectation for students on their off days?
On their off days. Okay. The homework for this class is not very high. I was just asking the students before, I was hoping they could answer the question for me, but they're saying about 30 minutes to 45 minutes when they have a homework set due. And that may be because we meet 3 times a week. So they'll have the night and then the next day to do it. So
that's great. Thank you. While the presentation was going on, I put some links in the chat box. I know Ms. Joslin shared with you the text for the introductory physics. There is a link also where you can explore the Novare science curriculum. Another link that I put is John May's book, From Wonder to Mastery. This really talks about, in terms of our style, or as he calls it, the transformative model for science education. That's what we follow. That's also another great resource if you're exploring Novare curriculum and specifically classes at Scholé Academy. I just want to make sure I haven't missed any other questions that might have come in. As I said, oh, go ahead, Ms. Joslin. Yep.
I had another comment too. Now, if you're interested in taking the honors physics class, there's more time involved with the homework. And it's a very challenging course. So the time, I prefer students to opt out. I don't like students to sit there for hours trying to work a problem, but it is considerably more challenging. So.
No, that's great and important to note the differences. I mean, our courses are listed online in terms of the science offerings. The honors physics course that was just referenced, that is the physics modeling nature. And when you look at the course offering, you'll see that that's a course for 11th and 12th graders, introductory physics. We accept students 9th grade and older. Anything else, Ms. Joslin, that you wanted to share about our science program, or just helping our families determine placement, or just kind of where to begin when they're looking at our science curriculum?
Determining placement, the math level for the intro is really Algebra 1. It needs to be a co-requisite for that, or a strong Algebra 2 student. We do a lot of unit conversions, which is just multiplying fractions and canceling out. Also exponents, working with very large numbers and very small numbers. We do it so much that they won't be afraid of it after we're done. The honors class, you need some basic trig concepts in there. If you're taking Algebra 2, you'll do just fine. You need a minimum of Algebra 1 in there. If they're not a strong math student, I'd want to test them before they got in there.
Sure. We do offer the placement assessments, especially for students who are joining our program that might not have been with us in earlier years. So that is something we talk about, our placement assessments in the student parent handbook. And you can always email directly any of our instructors to ask questions about placement as well. Just one final question before we go ahead and wrap it up for the evening. What about the amount of time for reading? How much reading is in our in this course and the other science courses?
The reading, we usually go 1 or 2 sections a day, and they're 2 or 3 or 4 pages of reading. There are a couple of supplementary books that I would like to put in, but they're fun reading. They're not very challenging. Occasionally, I need to bring this up too. Not occasionally, but every semester we'll have a paper due. So they'll pick a scientist, either a natural philosopher or autonomous, I can't say this, a modern scientist. So that would be just like a 5-paragraph essay kind of thing, but it would need to be referenced like a paper would be. So
no, that's great. Well, thank you everyone for coming tonight. If for some reason I missed your question in the Q&A or the chat box, please do email us at support@scholeacademy.com. And again, you can also email Ms. Joslin directly. Her email is online under instructors. There's a tab called About Us, and you'll find all the instructor page or instructor bios there. Thank you again, everyone. We appreciate you considering Scholé Academy to support your homeschool. Have a good evening.